Class, you are welcome to today's lecture. I'm sorry I was unavoidably absent last week. I hope we will be able to make the best use of the time remaining. Today, we are going to continue our discussion on parametric assembly. We look at parts as an assembly today. I sent a file to you, the file of my work, of my drawing on the internet video I sent. I don't know how many of you have been able to use that. I made some modifications which I will discuss, and I want you to use that as the base of your project. In your project, you are going to do a kind of assembly. You can do the engine assembly if you want, or if you have another challenge that you think is as good, that has the same kind of difficulty with kinematics, movement, and all those ones, you can. So if you suggest it, I can allow you. But remember that your project and all homework drawings must be in a file when you come to the final exam, because all the questions will be specifically asking you to do something about something you have done before. And the purpose is twofold. One is that if you did not do your work, I'll catch you there. So you pay for that error a second time. And that is going to be, I know somebody who got maybe 35/40 in continuous assessment and still failed the exam because he got 0 in the final exam because it was clear he didn't know anything. So I want you to be careful, because I may not be able to catch you if you do some things in your room, but I can catch you if you do it in the exam, because I will be there. And the questions will not be, you will not be able to just do as you like, because you are going to do it on the basis of what you have done before. If you don't know, if you just copied, you won't be able to answer the question. So you can be helped by your classmates, you can do group work, but after you have done it, make sure you learn it and you own it. Don't just depend on copying somebody's work and thinking you can do that and get away from this course. It's not likely to happen. You might be smarter than me, but I will try to catch you. If you succeed in getting away, good for you. If I catch you, well, there's nothing you can do about that. So we are going to go on. Today's scope, we are going to begin with the simple assembly like I discussed. We look at it again. We would look at the kinematical relationships. And these kinematical relationships are for you to practice, to understand, and to replicate. So you know how these kinematic relationships work. You practice it. You do it on your own. You understand it. And then you can replicate it and do more. FreeCAD parametric design strategy is based on bodies, parts, and components. You must understand the differences between these three. They are not things, they are not words you just use carelessly in FreeCAD. They have specific meanings. And it is the joint idea that enforces kinematics in parametric design. It's the joint. So you will have to understand what joint is, how it is implemented in FreeCAD. And when we finish that, using the existing drawing that I sent to you, my goal is that you should be able to draw that on your own. Don't worry if you copy what I have done. Copy as much as you can copy. If you copy and you do it 10 times, you'll be an expert. How good you are is not how brilliant you are, but it's how much you sweat. If you sweat, even something that is difficult is forcing you to sweat. A difficult CAD environment is actually better than an easy one. If they are both powerful, the more difficult one is better, because you will sweat a lot and you will quickly know what to do. Things that are hard for others will be easy for you because you have sweated it out. So the next thing I want you to do for the project is to venture into making the engine more realistic. Today, we are going to make the con rod more realistic. That will give you an idea of what to do to the other parts and the kind of results I want to see in your final project. Kinematics is number one, realism. For example, if you did not implement kinematics, you might move a connecting rod on your screen and it can pass through the crank or the piston, which is something that cannot happen in real life. You cannot pass through a wall, neither can you take a chair and use it to pass through the table. All those things that occur when you draw things. The idea of kinematics is to say, no, we will only allow things that are possible in reality, only motions, only changes in position that can happen. That is what kinematics is about. Kinematics is the geometry of motion. So it's geometry of motion that accords with what happens in reality. And in addition to the kinematics, we must also remember that logical assemblies, for it to be realistic, require possibility of repairs. If you do something and the only way we can repair it is to break it apart, then that is not something very good. That's not something that can last. Even the engine of a car gets fixed. A mechanic in Nigeria can casually open your engine, remove the piston, and put rings on it and put it back. Why is it able to put it back? Because there are bolts, there are things. So when we are assembling our engine or we are assembling our connecting rod or any part of it, we should be able to bring it apart using pins and bolts. So there are pins that connect components, that connect them to one another, and all those ones. So we are going to now add those realisms into the things we have. So we will start today, we will not cover more than the connecting rod. But by the time we finish, you will see how you can take a look at the other things and try to work with them too. Bodies. In part design, a body represents one single contiguous body, a solid, built with part design features. Exactly one solid at any given time, even if it has many features. So you'll see that the features could be pads, pockets, revolves, lofts or pipes, sweeps, extrusion, which we call pads, and all those things. Built using the part design workbench. A body is usually built using the part design workbench. You can build bodies from other workbenches, but most of the time we are going to be using part design. All features are created sequentially and upstream dependent. So what is the final solid in a body is called the tip solid. The final body is the tip solid. So let us say you have a drawing, a sketch, and you do a padding. As soon as you finish that padding becomes the tip solid. If you now make another sketch on it and you do a pocket, that pocket contains the results. So far, you have done pad, you have done pocket, you have done sketching. The final result is still called the pocket, and that is the tip solid. If you do a revolve, or you cut, the final result is called the revolve. That is the tip solid. If you do a lofting or piped, whatever, it is the final product of a body design that is called the tip solid, and that is the only body that remains at the end. That is how bodies are done. So this is the last thing. That is the last object. It is built using part workbench. All features are created sequentially and upstream dependent. Examples: piston, bracket, shaft, housing, even if complex, are bodies. They can be single body. A single body has a single contiguous solid built with part design features. We will see, we will explain that in practice soon. Important rules for bodies. A body cannot contain multiple separate solids. It must contain exactly one contiguous solid. That cannot be overemphasized. If an operation causes the body, if the operation is in a pad workbench, it will destroy one of the, if it cuts it into two, one of them will be thrown away. The portion that remains connected to the main body and discards anything that will become a separate solid, regardless of size. It is about connectivity. So it's what you are connected to the big thing, you are retained. If you are not, then everything is destroyed. Sketches and features belong to exactly one body. Here is a fundamental difference with fusion. For those who are still using fusion in this class, there may be, and I'm not stopping you if that's what you want. There are arguments for fusion. There are arguments for FreeCAD. I don't have any argument. They've thrown me out of fusion. I don't have enough money to pay, so I'm not using fusion again. I'm using FreeCAD. So if they're giving you free license, you can enjoy it while it lasts. Though my advice to you is that if somebody, after you have mastered the thing, can throw you out, then why not they take something and begin to put in your sweat in something that will be with you even after you have mastered it. Nobody can take your work and nobody can throw you out. That's my opinion. You are free, and I will not penalize you if you decide to work in a fusion, even though I will not help you either. So, we now talk about a part. A part is a container or grouping that can a grouping that can hold bodies. So a part can have more than one body. It can have other parts nested, can have datum objects, non-solid geometry, and so on. It has its own placement. It can contain multiple bodies, does not enforce the single solid rules that bodies enforce. It is used for organizing, positioning, and hierarchy. Think of a part as an assembly-like container or coordinate system. Examples: a gearbox can be a part containing multiple bodies, a sub-assembly, a logical grouping of components, or a coordinate frame for motion. I want to play this 6-minute video again. This 6-minute video that I gave you before, I'm playing it again, even though I did this work in Fusion 360. And in this particular thing, I implemented 1, 2, 3, 4, 5, 6, 7. I implemented 7 joints. You can see those joints on this side of what we call browser, on this browser or object or model tree in a FreeCAD. In Fusion, we call it the browser. So this is it. So these are the joints. Here, what you have here is what is called a wrist joint. The wrist joint is actually one in this particular case, is a combination of a revolute and a sliding motion that you will find there. Here is combination of back and forth, simple harmonic motion kind of motion, and then a revolution. Why one something moves back and forth. I just want you to see how it looks, and then we will go into another thing I want you to see here. You will see that the connecting rod here is far more elaborate and more sophisticated than the connecting rod that we did in the simple sketch. In this case, this connecting rod actually has 4 parts. Only 2 of the 4 parts are shown. The top of the main body of the connecting rod, and the connecting rod bottom here. And in this particular way, it's easy in Fusion 360 to show them in different colors. So then you have these holes here that you can use a pin or a bolt to use to join the two together. This is a very practical thing. If you have a connecting rod that doesn't have this, that means that if you need to replace it, then you have to break it. But this one, if you need to replace it, you can just remove it by removing these 2 pins, and you can disassemble it, and that's it, you put a new one. That is what I mean by building realism into your drawing. And this is a far more efficient connecting rod than the one that I will show you again. And so what we are saying is that you can change the connecting rod in that one to something as sophisticated as this and be changing those parts gradually until you can get a more realistic implementation. So let us just take a look at this again like we did before. Okay, I'm unable to change the volume, but what I'm saying here is that you can see that the connecting rod has two components. You can see that this is moving up and down, and then it is like moving like a wrist on this side. This one is go in circular direction. This is a more realistic connecting rod for the purpose of maintenance. The rotating motion is caused by the crank, as you will see. So you can see the crank now has been brought in. You can see it's moving in a circle. And then this one is going up and down and moving like a wrist. And you can see that even the crank is much more elaborate than the stator you had in the single engine that you have looked at. So the piston moves up and down because of a cylinder. It's inside the cylinder that compels it to move only up and down. Mm-hmm. Mm-hmm. So it moves it moves up and down. Mm-hmm. Okay. So this is representing this and the cylinder are representing the engine block, and they are fixed. So that's enough. What I want you to see is that you can see that, first of all, you can see that our connecting rod is more elaborate. You can see that the piston here is also more elaborate. You can see the position made there for the piston rings, and you can see where the pin is to be held. Okay, and there can be other things. You can put some things on here where the things that like the valves that open and close, and so or the space for the firing of the spark plugs to occur. All those things can be done here. So this may not be a flat surface. The surface here may contain space for the push rods and some other things, so that there will be no contact with those things when you are using this thing. So today's class concentrates on the collecting rod. A look at the above clip shows a few ideas to improve the other components. The piston can have slots for more rings as shown for some rings. It may also include a pin holder section inside it. Engine and cylinder and stator are in reality a single stationary part with circulation holes for cooling water and also passages for lubrication. The crank, as the number of cylinders increase, becomes a shaft that can be held down at critical nodal points. For after you have made a single engine, you can decide to turn the whole thing into a V engine where the engines are not all in line, and that is that's something that can be helpful. Yet this example is still elementary. More realism and improvement can be added even to my own example. If you search from the internet, you will see several things other people have done, and you will know more about an engine. Even though this is going out of fashion, electric vehicles are order of the day. So why am I still taking you backwards? I'm not taking you backwards. I'm just trying to let you see how we can use our drawing to implement kinematic constraints. And the engine of a car is one of the best ways to illustrate that. It's a very practical thing. There are many other things, even a camera stand. And there are several things you have in the house, like that have rollers and bolts, things that show like even a vice. There are so many things you can do that require kinematic constraints. But we are just making sure that these are teachable moments so that you can see how this thing can be done. If you can do it, if you have the expertise to do it now, you can do it in several other ways at your own convenience. Okay, so what we are going to do this morning is that we're going to move from the connecting rod on the left to the second one, to the third one, to the fourth one. You can see that it is the same connecting rod that we just continue to either add or subtract features from, that moved it from here to here. Even this simplest case can be a little bit of a hot potato, can be a bit difficult to do, because these small bends that you have here are not actually optimized for FreeCAD to easily do. It doesn't take more than 5 minutes or maximum 10 minutes to do this in Fusion 360. It can easily take you 30 minutes to 1 hour to do this in FreeCAD. Does that mean that Fusion 360 is better? Of course, the GUI of Fusion 360 is better developed. They've been in the market for close to 40 years or longer. They've been in that market for 40 years. FreeCAD is only 12 years old, I think. So they are still behind in the GUI. But again, those beggar has no choice. Those of us who do not have the free license do not have a choice. But those of you who have the free license, you can choose whichever one you like. Free Fusion is given to you. But what I can assure you is that anything that can be done in Fusion 360 can be achieved in FreeCAD. Initially, it will take longer, but as you are more conversant with it, your time commitment will be getting slower and slower. So I would do this from scratch here into this class, and I would almost finish this, and then I will leave it to you to do this and this. So by the time we do this and we have basically done this, you will immediately see that these are just very, in fact, you do not even need to attach these things to it. You can create this as separate components and assemble them. So that is even the neater way to get this one done. If you do it as a component, so the components, so you can see it is just now to retain this and add this as a fixed component at the ends here while doing a slice. At the slicing that you do here, again, there are several ways in which it can be achieved. Now, so what I will do, I will just show you, because the feedback I'm having is that many people have very great difficulty in getting their drawings to grain. It seems as if this constraint thing is just so elusive. So I am just going to show you how to draw this thing so that in about 2 minutes after you've started, everything you have on your drawing will be green if you just follow simple instruction. So to do it, just take a plane. Here I use the ZX plane or XZ plane, and I just move to the center and create a center circle of diameter 73. So if I do that, this turns green immediately. There is no, and then I go up, I go on top of the line, and I make sure I retain the line. And if you are still on the line, you will see a curve tool. If you don't see that curve tool, don't press. If you press the thing when the curve tool is showing without moving it, the point will be on the line, and you can do your circle of radius of diameter 40 here, and make sure that the distance between the two centers is 50. Once you've given the diameter of the circle and the distance of the centers, this also will turn green. The next one, again, stay along the y-axis. If you miss it, no problem. You just click the center, click this, and use the horizontal vertical constraint, and it would do it again. Make sure this is 20 and the distance of centers here is 100. This will turn green. If you do that lastly, and you make sure that this is 32 units in diameter and the distance of the center is 30, all these 4 circles are green almost on contact without any problem. Once you see they are green, you are now going to add 4 more circles. Well, I made this, the ones below 70-70 and the ones on top 40-40. You can't go wrong. If you increase a little, you can make the one on top here 60-60, and you will see when you are doing it why I said so. If you do that, all you are now going to do, since all the 4 circles, all the 4 original circles are fixed, all you need to do is to now force this one to be tangent to these 2 circles. Once you make it tangent to the 2 circles, the circle will be fully constrained and it will turn green. Similarly, let this one be tangent to this, it will turn green. Let this be tangent to this, it will turn green, and this. So you shall have had on the drawing table, on the drawing canvas, 8 circles that are all green. So you can clap for yourself that you could do something within 2 minutes and you are green. The next thing is to draw a line to this one, between these 2, that is, and let that line be tangent to this and tangent to this. Once you do that, tangent to this and tangent to this, they also will turn green. So after you have done that, you are just going to now trim off. You're going to use a trim tool to trim off the parts that are not needed. If you do that, you are going to get something like this. Again, FreeCAD is notorious for removing all your constraints when you are just trimming things off. Don't worry, it will look something like this. Making the 4 circles tangent to the nearest neighbors, set the entire drawing green and fully constrained. After setting the circles are tangent to each other, to each near pair, and drawing tangent lines, trimming extra lines lead to something close to what we want. Unfortunately, when I now tried to pad this final drawing, I kept getting the kind of errors you've been getting. Wire not closed, wire not closed, wire not closed. FreeCAD deletes dimension after symmetry constraints. In Fusion, much less work will be required to do basic conrod at this stage. But here we are using FreeCAD, and it's still going to work. So just be patient. So what I then decided to do is to start a new sketch. In my new sketch, let me just go back to that previous, since this one didn't behave, and it was giving me so much problem. So I did a new sketch and I projected in the same body. I projected all this, I projected this part circle, this 3/4 circle, this 3/4 circle with their ends. So 3/4 circle with their ends. And then this point, this point, this point, this point, and this line, and this line. I projected those into a new sketch. When I projected those into a new sketch, you can see the things that were projected. The lines that are projected are all magenta. And the points that are projected are all red. Or, I don't know. At least that's what it looks red to me. So, with that, the only things I then need to do is to use to put some curves here, 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 here. So the center of the curves. So how did I get this? I use a 3-point arc. You choose this point, then you choose this point, and then you choose a point near the middle. It will put the center away here, and it will draw this arc. Similarly, it will draw this arc. Here you have this one. The other one is at the end here. What you need to do is to make sure, if you want to ensure symmetry, you can make these 2 points symmetrical along this line. Once you make them symmetrical along this line, they are symmetrical, and you can now, because this is still not green, you can move this and you can change the shape of this line by moving this or this. So, and the same thing will happen below here. Once you have done this, so we simply start another sketch inside the same body. In the new sketch, we need only 4 edges. 1, 2, 3, 4. And 8 points. 1, 2, 3, 4, 5, 6, 7, 8. So forget about all the other things that are giving us problem. We've got the things we need. And there, this now is something that can be padded with no problems. Even without turning green, it can be padded. And when you pad it, it will not complain, and that's it. So that could help you to see the kind of things you should do when you are having those nasty wire not closed errors. So with these projections, we obtain the sketch shown. Homework: make the rounded parts symmetrical on all 4 sides. These are rounded parts. 1, 2, these two are symmetrical. These two are symmetrical. Just make sure in your own drawing, make them symmetrical. And compare the 2 sketches, tell which is superior. That is, when you finish this one, you compare this sketch to the previous one and then tell me which is superior when you have done the 2, and tell me why. Which one would you prefer to use? Even if this one did not give us the error of no wires closed. So that is it. So the next thing I did here is I add a path inside this place. I added this path. How did I do this? Let me show you how I did it so that you might want to do something like that yourself. So while you are here, you can do that arc here very easily. You do a 3-point arc, choose this point, and choose a point below. That will do you an arc. Yeah. Same thing, 3-point arc here, and somewhere in the center will do you another one here. So with that, you can take that newly drawn arc, this point, this vertex or this edge, and they will form a closed path. You can therefore go and offset that. You offset them inwardly. If you offset it inwardly, after you have done it, you are going to get something like this. After you got this, you can then remove the newly added arcs, and that's it. That's how you get this. Once you do that, you'll see that you now have something that can be extruded. What you can extrude, I just extruded it for 10 units, and I got this. Usually, in this particular case, you are likely to need to do it for 15 units. Now, let us compare to what we were trying to do. You will see that we have not yet got what we want. We have gotten this part of it. We have gotten this part of it, but we have not gotten these protrusions here, and we have not gotten this small end that is bigger than this thickness. We have not got that. Let me see whether I can get a feedback. I'm not able to get a feedback, so let me just move on. So at that point, you can also remove material. So this particular thing here is for removing material at the center. Why? We remove material at the center because simulation studies show that center area is not carrying a lot of load. So if you redistribute the load to the ends, it doesn't really affect much. And it is a very powerful way to end your something. So that is the internal offset modification of this. That's what we created here, and that's it. Okay, so to get to this one, what did we do? What we did here is to add another sketch, or we can add, what I did here is to have another circle of radius 60. This inner circle is 50 in radius. Do another one of radius 65 and concentric with it, and redo this circle here. If you redo this circle here, you can then choose a padding of those. It's a different sketch. You do in that sketch, you create this, you create that, and you create this, and you create that. And when you do the padding of that, you get this or this. Well, that is it. And you will agree with me that this thing that we have here is now looking close, if not exactly the same as what we have here, which is one of the things we set out to achieve. So that is it. I think you should be able to achieve that with ease. Adding another two-sided pad at the small pin of the connecting rod gives the expected result shown here. The dimensions of such connecting rod is obtained after a serious amount of analysis of the dimension of such a connecting rod, that is, how much hole should you put in the middle, is obtained from simulation. The largely empty space in the middle part of the linking straight portion can be shown to be optimal. It's optimal and it saves material, it saves weight. So it's a superior connecting rod when we do scenario analysis during continuous mechanics simulation. Now, we can continue by going to create this type of structure, this type of sketch at the end on the XY plane and extrude it. We can do it and extrude it and do a symmetric padding. When we do the symmetric padding, what we did here is to do what we did is to make a polar arrangement. You can do a polar replication. You have two bodies and you have one on each side. You can do it that way. That is one method. Another method is to create. You can create a kind of option for slicing, splitting, and fragmenting. A body can only contain a tip solid. It is called tip because it is the result of your final feature operation. This usually is the end of a sequence of tip solids that each feature resulted in. Here, we want to break the tip into solid fragments. We want to create solid fragments. We shall continue to be interested in two of these fragments while the others are to be discarded. Picture here shows the current tip object as we prepare the cutting tool to split it into fragments. This cutting tool will be created on the datum planes that we created at plus or minus 26 along each plane and so on. And we can refer to this plane directly. So we can create this. And then we create a cutting tool, and we call it quarter one and quarter two. If you look at my model tree, you will see this. This is the body. It had the original pad. Then we padded again. Then we padded it second time to achieve what we had there. Then now we have a cutter. A cutter is simply on the datum planes that we have shown, and we create an extrusion or a padding that is very thin. This padding can be as thin as 0.001. So that is it. Those are the objects that we are going to use to cut. Okay. So we have embodied cutters 1 and 2 by padding large rectangles on these datum planes created inside the bodies. We made the cutters very thin because they are knives. And remember, when we want to cut, who doesn't like a sharp knife? Again, we may want to cut the thing into the main body and the head. The third cutter is different in two ways. It was created on the coordinate XY plane, unlike the others that are created on the datum plane. This demonstrates the fact that datum planes are only references. If you can create the references in some other way, maybe you do not need a datum plane. So we made this, whereas the other two cutters were rectangular, this one is circular. In this case, we already know how to get at the coordinate planes because the XY construction plane is always available. So you don't need to create a datum plane on it. No need for more data planes. A round cutter for a change. We hereby demonstrate the fact that our cutter does not have to be rectangular. A circular cutter will do just fine, as we have done here. All we really need is that the cutter body dominates what is to be cut. It's bigger than what is to be cut. Once that condition is met, we are ready to cut. If we allow our cutters and the object to be cut to all show, this is what we have. So here we have the main body, the quarter one, quarter two, quarter three, before we invoke the split tool and generate our Boolean fragment. So it will fragment this into several Boolean pieces. And it is now for you to pack, to take the ones you need. Yeah, of course, I know you don't need this here. You don't need the one there. You need this middle part and the bottom part. Those are the only things you need, and you can continue. That is one method. Another method is to just, first of all, do a pocket. You can do a pocket that just removes that just does a shaving for your connecting rod. If you shave both sides, if you do a rectangle on this side and one on this side in the middle, you can just pocket on both sides, and it will cut it like this. The advantage of doing it this way is that you do not go into plenty torrential here. You just, once you finish cutting, you can draw this separately. You can do this as a separate object and do this as a separate, because it's the same object anyway. If you do this as a separate object, you can get this by assembly. So I leave this to you. If you try it out and work among yourselves, and you should be able to do this remaining two just that same way. So where are we? Okay, components. A part is a container that can, as an entity, participate in an assembly. A component is a reference to a part. You do not assemble parts. It is components that are assembled. The structure of FreeCAD allows you to design ones, that is the body, organize the parts, and reuse as many times, which are components. So you do your design in the body, you do your organization in parts, and then you reuse as many times as you like in components. So once a part is defined, you can bring several copies of it to an assembly, and then you can then move them about, and use joints to constrain them, but they are still the same part. You can make bodies as single tip solids. Bodies are organized into parts. Components take references to parts, and several references can be made. Assembly and components. In the FreeCAD workbench, the assemblies you get are assemblies, not of bodies. And I cannot overemphasize this. You are not assembling bodies. You cannot assemble bodies. You cannot assemble parts. In your assembly workbench, you must bring the parts in as components. And the components are simply references to the parts which contain the bodies. A joint is created between two components. In our FreeCAD test example, which I've already sent to you, and I will just take a look at in this class. So components reference their parts more than once. For instance, cranks and pins do this. So each is still referring to the same part. If you make any change in the body, it reflects immediately in the components, because the components are just pointing attention to those parts. Let's take a look at some of the joints in free test 001. I think we have gotten to a point now where we can take a break. All right. So let us go to the real con rod, and I will just want to show you something on that one. So if I come here now and do an edit of this sketch, I think this is sketch 01. Edit sketch. So this is how, after we have started, if we start a new sketch, let's see the model, start a new sketch, we remove the old sketch, but we bring in this, and this, plus these points. We bring all those things in. We have the things in magenta. And then, how do we do this? How do we draw this line? To draw this line, we just take the 3-point arc, arc from 3 points. When we choose that, we pick here, here, and somewhere here. And then after drawing it, we can turn it green by giving the coordinates of the center and the radius. But sometimes, in this particular case, sometimes it is good to leave it. And the advantage is that, for instance, this point is movable. Because this point is movable, you can see its effect on that one. So you can see its effect on that, and that is true for all of them. You move it, you can see its effect. And like I told you, if you do a 3-point arc here, here, and somewhere around here, you have this, and you can select that, this, and you go somewhere around here, you will see this is it. This is the offset. That's the offset tool. So with that offset tool, you can offset it inwardly and get this, and then remove the newly created arcs, and you get this. And once you finish with that, and you close the sketch, when you finish with that, you close the sketch, and you close the, if you turn off the sketch and you turn on the pad, you turn on the body. So that is what results from that. And then you can see the final thing there. Okay, so we can also go to the older thing, which is the free test, which I sent to you. If we make that, if we give it the focus, one thing I want to show you, the fact that this assembly is complete doesn't mean you can activate, it doesn't mean you can use it. For instance, if I try to move this, if I try to move this now, it doesn't move. And that's what is likely to happen when you try to move the copy you have. If you try to create the motions or the kinematic relationships, nothing happens. And then you'll be wondering, and I too was wondering, because that is not the way it behaves in something like Fusion. Once it is moving, anytime you touch it, it moves. But in FreeCAD, what you need is to activate the assembly. To activate the assembly, you just double click on it. If you double click on the assembly is activated, and then from that point on, you can move the, you can get the kinematic motions without any problem. What I want to show you here as to the changes that I have made, for instance, you will notice, let me make this one a little bit bigger. You notice that between this static object and this part of the rotor, there is a pin that comes from here and ends here. There's that pin there. So that pin is there. There's another pin that starts from here and ends here. Okay, so those two pins are there. And let me show you another one. The other one is easy to see if we remove the cylinder. If we remove the cylinder and the piston, let's see. Okay, you can see if you remove the cylinder and the piston, you see the piston pin. So that when we move this one here, when you are trying to move this one like this one is moving up and down. And in the example I gave you that I linked for you from the web, they didn't put something like this there. And the question is that a good idea or a bad idea? It's a very bad idea. Because if you have tried it, you will see that sometimes these motions fail. The motions are more reliable when there is even though the motion is abstract. Once you set the places that are supposed to be in the joint, the motion will be made, but it is not reliable. So when there's a motion, try and put the physical object, because that's how FreeCAD works. FreeCAD is more reliable when the physical object that connects this one to the piston exists. And another thing you will notice is that there are joints. I will just want to show you one or two of those joints. Let's bring back the things that I turned off. I turned off the piston and I turned off the cylinder. So both of them are on now. So if I go back to the joints, first of all, let us look at the joints one by one. This joint is grounded. Nothing happens in the grounded joint. No, nothing happens. But let us look at the revolute. You can see the revolute joint. Once I turn it on, look at what is happening here. The one arm of the crank is connected to the connecting rod, and it's also connected to the piston. All of those things are not available for that revolute. So the only thing that are full are this revolute joint is affecting this second arm of it. Let me just do it again. So the things that affect the joint are, let's see, the things when you take a joint, don't know where that sound is coming from. So take this problem. Well, this thing may have hung up. I don't know why it is making some unnecessary noise. Let's see. I can't see anything that is wrong here. Let me go back. Let me take something else. And go back here. Activate the assembly. And then, well, unfortunately, the program has hung up and I cannot settle that now in class. So I will go back again. But before I go on, please, class, there are a number of people that have been giving us, no, that's not this chat, that has been putting their names in the chat book. First of all, putting your name in the chat book does not assist you in any way. If we want to know whether you attend the class or not, we do not refer to the chats to get that information. We don't get that information from the chat. Let me just mention some names. Adebayo, David Adegoke, Odeleke, Oluwaleke Anthony, Akinkulehin, Oluwaferanmi, Oluwadarasimi, Aina, Daniel Boluwatife, Shodade, Oluwatobi Caleb, and Odeninde, Obafumi Systems, Abolaji Kende, and all those Olodorabatas that are just wasting time and typing their names. And some people do that every time. From now on, I'm going to be removing marks for putting your name and your ID on the, I will remove half a point. So if you want to be losing marks, keep doing it. Because I don't know what tests to do to people because they don't obey simple instructions. We don't need to be, when I see there are chats in the chat room, I rush there only to find out that it's just some Olulu Rabata that just put their name and didn't do anything. The chat room is for questions or comments on the class. So I will go back to the slides now to finish to this class. The joint I wanted to show is the parallel joint. There's a parallel joint between the two arms of the crank. That parallel joint is what forces them to move together. Because when you put a parallel joint, it means that those things must remain in parallel throughout their motions. And that is a joint that I'm not familiar with because such a joint did not exist in Fusion. I don't know whether it exists now. It's only a FreeCAD that I've seen that joint. And it's a very powerful feature of FreeCAD. So when you have two things that must move in tandem, the only way we used to do that in fusion is to make them fixed to each other. In FreeCAD, you have the other choice of making them parallel to each other. Because sometimes some CAD systems, when you make things fixed to each other, they must touch. So that means that you cannot, because you may want things to move together without they are touching each other, and that the parallel joint is a very good one for that. So when you activate the assembly, in order to demonstrate the motion. Select a particular joint. You will see the objects joined by that feature. All other objects are made transparent to distinguish them from the things that are affected by the joint. So take a look at my drawing, take a look at it, and then see whether I will try and now improve the individual elements and come up with a superior engine for your project. Okay, joints can be virtual or real. It is possible to request a joint between the center of the small end of the connecting rod and the pinhole or the piston component. That joint is virtual, and it will likely work, but it may not work as reliably as if you actually add a pin to it. If you add a pin, the pin makes it more real, and it is actually more stable in FreeCAD. So it's also possible to create a real pin linking the two pieces as we have done here. In the internet video I referred to last lecture, virtual joints were used. They can be very unstable in FreeCAD. Real joints are more stable and they are encouraged. Multiple bodies in a part. We said earlier that a part can have more than one body, but a body can have only one single solid. Take, for example, the connecting rod. We can have 4 bodies inside the part. What are the kinematic relationships? If you have parts inside the body, are there kinematic relationships between them? The answer is 0. There is no guarantee that FreeCAD will implement any rule of motion. So you can move them and they can enter each other, they can disturb each other. So there are no kinematic relationships between the bodies in a part container. Joints can only occur between 2 components. In order to ensure proper kinematics between elements in a part, they must each become components, even when they are inside a part container. It's a matter of experience, preference, and interest, whether you arrange multi-body parts or you let them be in separate parts. Some people, because of the inherent relationships, they want them to be in the same part. But some other people, since you have to implement kinematics through components, better just make them different parts so that they can come in as different components as they should be. I prefer to arrange them as individual parts so that you may have 4 components in 3 parts that make up the connecting rod subassembly. Can you list them? In this particular case, there are 4 components, but there are 3 parts because 1 part is repeated. When you assemble a subassembly, the internal joints determine how they relate in motion. So the internal joints are the joints that you made between them when they are together in their subassembly. The connections between them are not automatically fixed. Project. Now, this project will be submitted a week before the exam. And what you need to do is to replicate the free test 001 that I've given you on your own. You do it and you keep a copy and submit a copy. Work with one another, but do not copy from another person. If your drawing has exactly the same naming, the same order, the same everything as another person, I will assume that you have just copied because 2 people think differently. You will need your own work in the final exam. Questions will be asked that only those who do their work can answer. You will not be able to cheat in the exam. When you are asking other people to help you outside the exam, you are not cheating, you are learning. It is good to learn. But to consummate your learning, you should be able to do those things yourself. Otherwise, you have not learned anything. Number two, create more realistic implementations of the engine parts. I gave you an example now of how we can change the connecting rod and make it a sub-assembly in its own right. You should also look at the other parts and look at different. You can choose a different project provided it is as elaborate as this one. It is an assembly in its own right. The con rod bottom or head, if you like, 2 pins. 4 bodies in all can be assembled or used in their positions. Improve the other components and come up with your own assembly. The grade for the final project is 30% of the course. I am not sure whether there will be more than what I've given you now, but the marks you will have before your final exam from the project alone is 30% of your final marks. And you are also to bring your project to the exam, because I can ask you to do things that continue from where you have stopped your project. Disclaimer: we have used examples such as bench, concrete bench, reinforcement, volute, impeller, turbine, engine parts like crankshaft, connecting rod, piston, cylinder, and so many things. It is not our purpose in this class to teach all these things. This is not an authoritative course teaching those things. That's not what we are doing here. Instead, we are using them to show how engineering components and assemblies can be achieved in your drawing. These efforts are needed for analysis and simulation. Mastering this should be immediately useful in your other courses, and you should be able to make actionable graphical production of virtually any engineering concept you have. Whether they came in your courses, they came in your projects, they came in your observation, and they came from your interest. The whole idea of learning to do graphics is that you should be able to give a graphical representation of production of any engineering concept or any engineering artifact or any component or anything you see. You should be able to draw and give an actionable graphical production of virtually everything you can think of. What do we mean by actionable? First of all, a photograph is not actionable for the simple fact that if an idea occurs in your mind, you cannot take, no matter how powerful your handset is, you cannot photograph somebody's mind. It's not possible. You can't photograph somebody's mind. You can photograph the person's bones and so using X-ray machine and such things, but you cannot photograph an idea. But you can turn even an idea that does not yet exist into an actionable graphical production in FreeCAD or Fusion or any of the CAD software we have looked at. What is actionable? A photograph, for example, of a beam is not actionable. You cannot change its geometry from a photograph or examine if it will become stronger. You cannot alter its material composition and study how that changes its behavior under loading. You cannot change the load it carries. You cannot alter the ambient environment that governs the temperature conditions and wind effect. You can't do any of those things. A FreeCAD parametric design is actionable. It is designed to do all of the above. In engineering simulations, these are the exact things we will be trying to do. It is the most fundamental core of engineering education. Incarnate any concept, copy any idea or artifact, apply the laws of nature to them, and create realistic scenarios abstractly. Compare the results. It is on the basis of these actions that prototypes can be built economically. And that is the reason why you are doing FreeCAD. Well, that is all I have for you today. And if you have questions, you can send them to me in somehow, I don't know. You can send them to your class rep who will give them to Mr. Ayode. But I do not want people in the class to be sending me direct messages. I don't want. In this particular, so I think that is all we will do today. I want you to have a nice week. Do the drawings I've given you, and work on your project, and then make sure you keep a copy for the exam. Thank you.